Hello, today I will be presenting my project on a rating prediction model using the Amazon Movies and TV dataset. The main goal of this project is to build a prediction model which will predict how a user will rate a movie based off of different features in the review. Throughout the presentation, I will be walking through the dataset, the approaches I took for modeling, metrics I use for evaluation, and analysis of the results. Let's get started. So the goal is to predict a user's rating from 1 to 5 based off of the inputs of the user ID, the item ID, and the review text. To evaluate the models, I'll be using a train validation test split and use the root mean square error as the primary metric, along with the mean absolute error being the secondary metric. I'll be comparing the model to several baseline models, which will be the global mean, the user mean, the item mean, and a user item bias model. Now for overview of the dataset, the Amazon Movies and TV Show dataset contains a catalog of user reviews of movies and TV shows. Each review contains a numerical rating, a title, a text field, a user ID, item ID, timestamp, and metadata. I've selected this dataset due to the fact that it contains both structured and unstructured features. This will make it a strong candidate for feature engineering. For pre-processing, I kept the key fields that is required for the model, being the user ID, the item ID, the rating, the review title, and the review text. I created a full text field by combining the title and review text, since both contribute to the sentiment and context. The dataset is already well structured, so pre-processing mainly involved selecting the relevant columns and standardizing the columns. I'll be quickly walking through the code and what I did for these. From the top here, we've just did a pip install, imported the various modules I needed, and then I loaded up the JSON here, then kept only the columns that we will be using here, and simply just standardized the columns. Now to some observations we made after plotting out the data here. First observation is the fact that reviews skew heavily towards 4 and 5 stars. This positivity bias is common among user-generated reviews, as users are much more motivated to leave a rating when they like a product. The skew also means that a simple model predicting values like 4 to 5 will look really good. Now this is the plot in question here. You can see most of the reviews or the ratings centered around 4 and 5. Next observation that I made is that the user activity follows a classic long tail pattern. This means that a small number of users write a lot of reviews, while most users only write a few reviews. This means that a collaborative filtering approach will struggle for low frequency users, and that regularization will matter. You can see here, most users only have a few number of reviews, while a couple of users have a lot of reviews. We find a similar pattern with the item popularity. Similar distributions, meaning that most movies have very few reviews, and a few movies have a ton of reviews. Here is the graph quickly, and I have the code on the right here to plot out these graphs. Next, we'll be moving on to the modeling approaches. I implemented 5 models in total, ranging from trivial baseline models to more complex models and hopefully more expressive ones. Our most simple model is the global means model. It simply predicts the average from the training dataset for each prediction. Next would be the user mean and item mean models. They predict respectively each user and each item's average rating from the training set. These models are intended to be heuristic in nature and used for comparisons and sanity checks. However, I did find that the user mean was a better predictor than the item mean. Next, I had the idea of combining the last 3 models that we just discussed into a 4th model here. Now this model combines the global mean, the user bias, and item bias when making a prediction. The idea here is that it should capture tendencies such as a generous reviewer and a well-rated movie or TV show. However, due to the distribution of our data, with most movies getting very few reviews and most users providing very few reviews also, this in practice means that this model does not perform significantly better compared to the user bias model. Next, on to our primary model here. For this model, we applied TF-IDF, also known as term frequency inverse document frequency, in order to capture the information that is contained within the text. Now, TF-IDF converts a raw text into a higher dimensional numerical representation by counting how often each word or phrase appears in a review, while downweighting common terms that appear across many reviews. We use unigrams and binograms so the model can learn from both individual sentiment words like amazing or boring, as well as short phrases like highly recommend or waste of time. We also remove stop words, limiting the vocabulary to 20,000 to the 20,000 most informative terms. The result is a sparse feature vector for each review that captures the key language patterns associated with different rating levels. These engineered text features are then fed into a ridge regression model, which learns how each word or phrase contributes to the final numeric rating. This step is responsible for most of the performance improvement because the textual context carries strong sentimental cues that correlate directly with how a user rates a movie. Now quickly on to a walkthrough of the code here. So as you can see, the top snippet here, we simply are splitting the data into test and training sets. Next, we are just implementing the global user and item means here. And then the next part would be the global mean plus the item and user bias prediction. And lastly is our TF-IDF implementation here. Now on to the evaluation of our models here. Our MSE and MAE quantify how far our predictions are from the true rating. Therefore, we are looking for a lower value, which means the model performs better. We will be measuring both validation and test scores to ensure that our model generalizes well. Here are the validation results. We can see that the worst performer here is the global mean and the item mean. The user mean is a slight improvement, and the user item bias model does not provide significant gains in this dataset, likely due to the sparsity of the items. However, the big improvement here comes from the text-only ridge model, which drops the root mean square error from around 1.17 down to 0.76. Here are the test set. We see a similar behavior here. Global mean around 1.2. The user item bias is a slight improvement, but the major improvement here comes from the text ridge. The close match between validation and test performance here indicates that our model does generalize well with minimal overfitting here. These results line up with the findings from previous recommender research. Review texts contain rich sentiment signals, and users often justify their ratings directly in the text. So linear models such as TF-IDF directly benefits from this information. Models based only on user IDs cannot leverage this context, especially in a sparse dataset. Prior works on the Amazon review data sets commonly use matrix factorization, neural recommenders, and review-aware models. Our results are consistent with these findings that textual features outperform pure collaborative filtering when there is significant text. Although we did not use any deep models here, TF-IDF plus ridge classification captures a significant portion of the text signals. Now there are a few limitations worth noting. Firstly, we did not incorporate any metadata such as category or price, which could improve item level generalization. Secondly, hyperparameters were not tuned extensively. And thirdly, our collaborative filtering component is fairly simple compared to other models. For future works, of course, we could include the metadata, and we can also use a transformer-based text embedding, such as BERT, for interpreting the review data. Takeaways from this project is that text features are the strongest signals here. User identity adds value, while item identity contributes less due to sparsity. Also found that a simple TF-IDF plus ridge model significantly outperforms collaborative filtering baseline, and overall found that this dataset is well suited for demonstrating how feature engineering can unlock predictive performance.